Vector algebra. I know, it sounds super complicated, right? Something you'd see scribbled on a dusty chalkboard. But what if I told you it's actually just a simple recipe? Yeah, a recipe that lets us precisely map out everything from a rocket's flight path to the forces in a game of tug of war. So let's break it down. So, first off, why do we even need algebra for vectors? I mean, why can't we just draw them? A vector is just an arrow, after all. It's got a length and a direction. Well, here's the thing. When you're dealing with anything that needs to be precise, like really precise, a simple sketch just isn't going to cut. You know what I'm talking about. Imagine someone scribbles a map for you on a napkin. Okay, turn left at the big tree, then go kind of that way for a bit. It gives you a general idea, sure, but it's not exact, is it? And that's the exact problem with using drawings to work with vectors. They're great for a quick look, but they are fundamentally imprecise. And this really gets us to two totally different ways of doing things. You've got the graphical method, using rulers and protractors, but it's always an approximation. The best you can do is limited by how steady your hand is. But then, there's the analytical method. This uses simple algebra to break vectors down. It's not a guess. It is exact. Every single time. So how do we get that kind of precision? Well, this is the big aha moment. We're going to stop thinking about a vector as just a single slanted arrow. Instead, I want you to start thinking of it like a recipe with just two simple ingredients, a purely horizontal part and a purely vertical part. And these ingredients, they actually have a name. They're called scalar components. All that means is they're the straight line distances you have to travel horizontally, that's your x-axis, and vertically, your y-axis. When you put those two simple numbers together, you have to find the exact length and direction of your vector. This is the whole secret to the analytical method. And you can see exactly what I mean right here. We've got this vector, A, just pointing off at some random angle. But we can describe it perfectly with just two simple numbers. How much it goes sideways, which we call AX, and how much it goes up and down, which we call AY. With a tiny bit of high school trigonometry, we can find these components and turn a vague arrow into a precise mathematical instruction. Okay, so if a single vector is a recipe, what happens when you have a bunch of them? This is where it gets really cool, because adding them together is as simple as just combining the ingredients. And hey, don't just take my word for it. The source material spells it out perfectly. You don't need any complex geometry. You just add up all the horizontal bits together, and then you add up all the vertical bits together. That's it. Seriously, it's that simple. So this all boils down to a super straightforward 4-step recipe. Step 1, find the horizontal and vertical components for every single vector you're working with. Step 2, add up all the horizontal parts to get your total x. Step 3, do the same for all the vertical parts to get your total y. And boom, step 4, those two totals you just found, those are the components of your final answer. Clean, simple, and perfectly exact. All right, enough with the theory. Let's put this recipe to the test with a really fun example from the source material, a full-on canine tug of war. This is the perfect way to see how this all works in the real world. So, picture this. 4 dogs in an epic tug of war over a toy. We know the exact force and the exact direction that Astro, Balto, and Clifford are pulling. So here's the puzzle. What single specific force does the 4th dog, Doug, have to apply to make it a perfect stalemate so the toy doesn't move at all? And here we go, step 1 of our recipe in action. We take each dog's individual pull and we break it down to its x and y components. You can think of this as the east-west pull and the north-south pull. All of a sudden, 3 confusing, diagonal forces just become a clean, simple set of numbers we can actually work with. Next up, we just add the ingredients. We add up all the x forces, all the sideways pulls, and we get a total of 150.3 newtons. That's the unit for force, pulling to the east. Then we sum up all the y forces, the up and down pulls, and that gives us 49.2 newtons pulling to the north. This right here is the combined effort of those first 3 dogs. Now, here's the key bit of physics. For that toy to be perfectly still, for it to be a true stalemate, the total net force on it has to be 0. What that means is that Doug's pull has to be the exact opposite of the combined pull from the other 3 dogs. So what does that look like? Well, if the combined force of the first 3 dogs is pulling with positive 150.3 in the x direction or east and positive 49.2 in the y direction or north, Doug's balancing force has to be the perfect opposite, negative 150.3 to the west and negative 49.2 to the south. He has to pull perfectly against them to cancel out their entire effort.
So, we take Doug's components, we run the numbers to find the total strength of his pole, and we get a precise, exact answer. 158.1 newtons. Not around 160, not somewhere over there, a perfect calculated value. Now that is the power of the analytical method.
And look, this method is so much bigger than just dog-based physics puzzles. This is the engine that drives so many different fields. It's how engineers figure out the stress on a bridge. It's how physicists map out invisible electric fields. And yeah, it's how video game developers program the realistic physics in all your favorite games.
So, what makes this method the absolute winner? Well, first, it's precise. It gives you exact results, not estimates. Second, it's totally scalable. You can add 2 vectors or 2,000 vectors, the recipe's the same. And third, it's a foundational tool. It's literally the language of anything that has both a strength and a direction.
So there you have it. We took messy, confusing arrows and turned them into a simple, elegant, and powerful recipe. We've seen how any combination of forces or movements can be calculated with perfect precision. It's a tool for predicting the outcome of any journey. So I'll just leave you with this question. Now that you know how to precisely calculate any path, where will you go next?